Hello, this is the highlight for the live lecture that we've done in our fluids course, and I wanted to record a take-home message from that particular lecture, and this is about our discussion of potential flows and how to classify flows into rotational and irrotational and what that means in terms of potential flow solution existence. So if the velocity of the fluid can be represented by a gradient of a scalar potential, then we can, in a 2D situation, we can define a stream function, and the velocity components can be derived then either from the potential or the stream function as derivatives of those. It turns out that the governing equations, the conservation of momentum, reduce to a linear partial differential equations. In the simplest case, Laplace's equation. And those equations, they are linear, meaning that if there are two solutions, then the linear combination of those solutions is also a solution that allows us to combine known solutions of simple flows, so-called elementary flows, into a representation of a more complex geometry. And when we plot the solution that we obtain analytically in terms of stream function and potential, we obtain what's called a flow net. A flow net is the family of streamlines, which are lines that are tangent to velocity vectors of any time at any point in space, and the family of potential lines. These are the contour lines of potential, constants of capital phi, the potential of the field. So the streamlines and potential lines are orthogonal to each other at any point in space. And that flow net has a very useful property. Even if the problem at hand cannot be reduced to a potential flow situation. For example, if let's say the airfoil we're considering at a high angle of attack and there is massive separation, then in the wake the flow will be viscous and not really tractable. Using this kind of theory, we may want to resort to CFD to get a numerical solution. In order to do that, we would need a numerical mesh of our flow field. And the very useful property of numerical mesh is orthogonality. So we would need grid lines that are orthogonal to each other at any point. And so one way of doing that is to solve the elliptic partial differential equations. One example of those is Laplace's equation. Find a potential in the stream function, even if we know that this is not really representative of the physical situation at hand. We could use that flow net that the potential solution gives us as the grid for solution of the actual problem. So more high fidelity CFD simulation. So that's one neat application of potential solutions. This is not to take away of usefulness of potential flow solutions themselves in the situations where they are applicable. So that is a surprisingly large class of problems that can be solved using those methods.